Welcome to my presentation on logical characterization of hybrid conformance. My name is Maciej. I'm from the University of Sheffield, and this is joint work with Mousavi from the University of Leicester. Our work is set in the context of verification of systems that exhibit continuous behavior. And these can be, for instance, control systems or cyber-physical systems that in addition have a discrete aspect, but the key element is the presence of continuous dynamics. Now, when we attempt to verify such a system, presumably we have some formal specification of its desired behavior, either in terms of a formal model or some logical properties. And the question is then, if we have a real system and implementation, when we consider it correct with respect to our specification. Now, in software verification, the situation is easier. We have a range of conformance relations, like for instance bisimulation, which operate on discrete setting, and they are exact in the sense that they require behaviors, values, propositions, etc. in the implementation to match exactly the specification. But for control systems and cyber-physical systems, this approach is typically not viable because, for instance, the real-world data that we receive, like location or temperature, velocity, it's measured with imperfect sensing devices, and then information is sent through imperfect channels that may delay the signal, etc. So the exact conformance relation may not be helpful in this case, and we may want to use instead some approximate conformance relation that allows for disturbances that has some tolerance bounds. Now some more detailed observations about the kind of conformance relation that we want to deal with. So firstly, because we want to work with approximate conformance relation, if a system produces some output signal, we want to allow for some disturbance in terms of the value of the signal. Now the second observation is that the system behavior may well be continuous, but we may be only able to observe it in particular time points, so we have a discrete sample of a signal. So we want our semantic model to cater for both behaviors, continuous and discrete. Well, to have a, let's say, an accurate approximation, it's not enough to approximate in terms of value, because the signal may be nearly matching the specification. But it may be slightly delayed or retimed. And in particular, if the signal has a steep gradient, then the very small changes in time may give rise to considerable jumps in value. So we need a separate tolerance threshold for time. Now the last picture illustrates precisely the kind of semantic model and conformance relation that we wish to deal with. Now these two behaviors, green and blue, are conforming, even though they are of different kinds and there is disturbance both in time and value. One of the main approaches in system verification is based on logical properties. We specify requirements in terms of logical properties in some temporal logic, and then we can either check if these properties hold on the entire system, or as in case of most of the complex continuous systems, we may just be able to test or monitor them on some executions of the implementation. So here we have a simple example, a formula which says that the signal will stabilize within some interval around value 2. Now, if we want to combine this property-based verification with approximation, with the conformance up to some tolerance threshold that we just discussed, then we would like to know if one system, the original system, satisfies some formula, then what kind of property can we expect from a system that is conforming with some particular tolerance bounds. So we probably need to somehow relax the logical formula, but we want to know to what degree precisely. Because we don't want to test for properties that can't be preserved, this is not meaningful at all, and we don't want properties that are too relaxed, too trivial, because then we lose the opportunity to do more thorough, more complete verification. So ideally, we want to have the so-called logical characterization of a conformance relation. This is when we know precisely which formulae are preserved, and there is always a formula that can distinguish systems that are not conforming. So at this point, we can state our general research goal. First, we want to settle on a semantic domain that caters for different types of system behaviors, both continuous time and discrete. So we also need a suitable real-time temporal logic and a conformance relation that allows for disturbances in both time and value. And having those, we would like to provide a logical characterization of the conformance relation in the chosen logic. So we want to provide a method to identify two conforming systems by means of logical properties that they satisfy. And just a quick outline of our solution that I will talk about. For the semantic domain, we define the so-called timed traces. For the logic, we choose a variant of metric temporal logic that we adjust a little. We use an existing conformance relation from the literature called tau epsilon conformance. And our main result is the characterization of this relation using a syntactic relaxation on metric temporal logic. A brief look at the literature that is most relevant to our work. There are a few temporal logics that handle real time. The one logic that is important for us is the continuous time extension of MTL called STL by Malar and Ickovic, and our variant of MTL can be seen as a generalization of STL. As for logical characterizations, they have been extensively studied for exact conformance relations on discrete models, and the seminal works are characterization of bisimulation with Henne-Similner logic. Also, Rob van Glabeck gave logical characterization of many other relations in his spectrum of semantics. For approximate conformance relations, I believe the first logical characterization was given by De Alfaro, Faelia, and Stulinga for metric transition systems and quantitative temporal logics. Compared to our work, they considered approximation only in terms of value, but not time. Now there are two articles that are particularly close topic-wise to our work because they deal with relaxation of logics with respect to both value and time. The first one by Deshmukh, Majumdar, and Prabhu deals with score-hod metric, which is stronger than the relations that we consider, and which is defined for continuous time trajectories. They define a relaxation operator for this so-called freeze temporal logic and prove the preservation for score-hod metric, but not the reflection property. So finally, the work that is most relevant in our context, the paper by Abbas, Mittelman, and Feinekos, in which they introduced the tau epsilon conformance, which we also use. They work in a more restricted setting of discrete behaviors, the so-called timed state sequences. And they also define the relaxation operator for MTL, and they show the preservation for a tau epsilon conformance, but the relaxation is not perfectly precise, so it doesn't guarantee the reflection property which is needed for characterization. Some preliminaries, to start with a semantic model. In our framework, the basic unit of behavior is a timed trace, which is a mapping from a time domain to a space of values. And we only make minimal assumptions that the time domain is a subset of positive real numbers, and the values form a metric space. Now, initially, on the article, we made the assumption that 0 belongs to the time domain, but actually it's not needed, and it's more desirable not to have this restriction. Now, more concrete behaviors like flows or discrete timed sequences, they can be formally defined as subclasses of timed traces, basically restrict time domains. Our notion of system in the article is very straightforward, and here I even use a simpler definition, which captures the essence of our theory, where the system is simply a set of timed traces. It's a simpler linear view of hybrid system. So on one level, it's very abstract, but it's also related to more pragmatic verification methods of dynamical systems, we don't go into branching structure of the system, but just execute and observe traces of systems and possibly compare them against each other. We also distinguish a special class of strongly finitely branching systems that contain finitely many timed traces. So note that this is a stronger notion than standard finite branching. To specify properties of timed traces and systems, we use metric temporal logic, which is a real-time extension of linear temporal logic. And real-time behavior is captured by annotating temporal operators with intervals. Our syntax has some special features. So negations are only at the level of propositions, and propositions and propositional expressions are always guarded with a temporal operator. So again, this is an optimization as compared to the article. It's a more neat solution. And there are special propositions for the purpose of relaxation as well. So when it comes to semantics, it's not entirely obvious how to define it for our timed traces, in particular for timed state sequences where the time domain is discrete. But what about the remaining timeline of all positive real numbers? So our semantics of choice allow to make statements about any point of timeline, not necessarily in the time domain. This seems to be a natural choice, but in particular when we check properties of two different timed sequences with different time domains, then we can always use the same time point of reference. For instance, in our semantics, we can make a statement that these two timed sequences both satisfy this formula phi at time 0, even though neither trace has 0 in a time domain. So there is no sample point at time 0. So this type of semantics allows us, I think, more precision, and it's also useful for the characterization result. A quick look at the propositional part of the logic. Propositions are interpreted over the space of values, and we can instantiate them, for instance, with STL-style propositions like this. But for characterization purpose, we can use the minimal type of propositions that involve comparing distance between signal and some value. So similarly as in the relaxation of Abbas, Mitterman, and Feinekos, we use these additional propositions. And to quickly explain them, if P corresponds to some set in the space of values, then P plus of epsilon corresponds to the epsilon expansion. And for P minus, we take the contraction of the set and then its complement. There is one issue regarding propositions because we allow to check if the formula holds outside the time domain. So if propositions are not guarded by a temporal operator, and then we test them outside the time domain, it may happen that both the formula P and the negation don't hold. So it's not very desirable. But the problem is really just for purely propositional formulae. So we can neatly solve this by ensuring with the syntax that propositions are guarded by temporal operators. Then when we write a formula, it's unambiguous. So we precisely declare what property we ask for. So for instance, with until, we ask whether P absolutely certainly holds at current time point. And with release or box, we ask whether there is no evidence that P doesn't hold. The main feature of MTL are temporal operators annotated with intervals, so time until and time release. For instance, until, as in standard LTL, has the liveness component psi. This psi needs to hold somewhere at some point of time domain within the interval. And there is a safety component phi, which must hold at any time point of the time domain until when psi holds. And release is a kind of a dual operator where the releasing formula psi doesn't need to hold, provided that phi holds in the entire interval. Now, when it comes to semantics for non-deterministic systems, in linear time logics, the standard semantics for non-deterministic systems is that a system satisfies a formula if all its possible traces satisfy the formula. And this is basically our definition as well. But there is another possibility. So we can take into account formulae for which there is an execution trace that satisfies them. And it's somewhat similar to characterizations of semantics in Van Glabeck spectrum and variants of Hennessy-Miner logic. So we also introduce this relation that system exhibits a formula if the formula holds for some trace of the system. So we have determined our logic, and now we move to our conformance relation. This notion of hybrid conformance, or tau epsilon conformance, was proposed by Abbas, Mittelman, and Feinekels, and it relates traces that are close to each other with respect to time and value. In our article, we also analyze in more detail the refinement variant of this relation, but I will focus mostly on the standard symmetric variant, which has nicer properties, appears to be much more well-behaved and useful. The definition works for general metric spaces, but to explain the intuition is best to consider a real valued trajectory. And there, if we have two-timed traces, and we say a trace like mu1 is a tau epsilon refinement of mu2, if every point in the graph of mu1 can be matched by mu2 within this tau epsilon window, tau in time and epsilon in value, which is the case here. Even though mu2 has this short spike, it can still match every value of mu1. On the other hand, mu2 is not a tau epsilon refinement of mu1 because the spike point can't be matched by mu1. So our main conformance relation is tau epsilon closeness, which is when we have mutual tau epsilon refinement of two traces, so they mutually match each other. And we also lift the definition to systems, so the two systems are tau epsilon close. And for each trace of one, we can find a tau epsilon close trace in the other, and vice versa. So we have specified our conformance relation and the logic. Now, how can we provide logical characterization of tau epsilon conformance? So in general, logical characterization is a method, a scheme, to provide an alternative definition of a conformance relation through the logic, where we know which formulae are preserved, and also all non-conforming systems can be distinguished by some formulae. How exactly we accomplish it is up to us, but we are interested in relaxation of properties, and this is our natural way to provide characterization. Relaxation is basically a syntactic transformation of a formula to a weaker formula. And if we have such a relaxation operator, then the idea is that we have characterization if, firstly, when a system is conforming, then we have preservation of formulae under relaxation. And secondly, if there is preservation under relaxation, then it must imply conformance, the reflection property. So here we can use either existential or universal interpretation of satisfaction relation. And for well-behaved relations, these are typically equivalent conditions, and in our case, both of them hold for symmetric hybrid conformance. But in the article, we also took a look at a less well-behaved preorder in which only the first condition holds, and this is how we achieve characterization there. But here I will only focus on the more important symmetric hybrid conformance. At this point, I would like to give you some technical details of the relaxation operator. It's a syntactic transformation on MTL, and like our conformance relation, it has two parameters of relaxation for time and value. And technically, we have value relaxation on the level of propositions and time relaxation in temporal operators. This is similar to what happened in the paper by Abbas, Mittelman, and Feinekels. The value part is straightforward. We just use the additional propositions that I mentioned earlier that correspond to expansion and complement of contraction. Now, the key question in our relaxation is how to relax a formula in terms of time. A time relaxation is handled through the temporal formulae, and one has to be careful and precise because temporal operators contain two components which are of opposite nature and for which we need different kinds of relaxation. For the liveness property, relaxation means expanding a certain interval, and for the safety property, relaxation means shrinking some other interval. And more specifically, let's assume that one trace satisfies the original until formula, and let's think what we can deduce about the tau epsilon conforming trace. So for property psi, we have an interval I in which it must eventually hold in the first trace, and in the conforming trace, there must be some point which corresponds to this point, where psi holds, but it can be shifted by tau in either direction. So we need to expand the interval where we expect psi to hold. Now, for the safety property, we need to reason the other way around. We are working with a symmetric relation, and so also in the conforming system, we have this property that a corresponding point must be present in the original system, in the tau vicinity. So if all points in the tau vicinity of a given point satisfy phi, then it will carry over modular relaxation to the conforming system. So this is true for all points in this shrinked interval, which is shrinked from the left by tau and from the right by 2 tau as compared to the point where relaxation of psi holds. This is because on the right-hand side, we have two sources of approximation. The point where phi needs to hold, but also point where psi holds. And in the corner case, psi may be shifted as far as here by tau to the right compared to the original interval. And then the safety interval is shorter in total by 2 tau compared to the original one. And if psi happens earlier, it is relatively even smaller by up to 3 tau in total. So this was some intuition how the relaxation of until works, and it has to be carefully syntactically encoded into the formula, which looks like this. Technically, we first need to shift the timeline forward by tau, and then the original until interval is shrinked by 2 tau into this one, and the rest is taken care of by relaxing the liveness part by 2 tau in both directions. And if the interval was shorter by 2 tau than 2 tau in the first place, then the safety part disappears. For the release formula, we have largely the same reasoning. Just the releasing formula is optional, it doesn't need to hold. And syntactically, the relaxation is actually simpler than for until, because we don't have the strong liveness obligation. So here is the entire formal definition of our relaxation operator. The salient points are propositions, and especially temporal operators. And the key result of our article is the characterization of hybrid conformance. We show that systems are tau epsilon close if we have preservation under our relaxation operator for both existential and universal interpretation of formulae. And here this direction really doesn't matter because we have a symmetric relation. Just a technical note, if we use the syntax with finite conjunctions, then the result is for the systems with finitely many traces. And for arbitrary branching, we need the infinite conjunctions. And finally, just a brief sketch of how we can construct distinguishing formulae for non-conforming traces. Suppose we have these two traces which are not conforming, but such that the refinement is missing just in one direction. So here, trace mu1 has a point in the graph that cannot be matched by mu2. So formula distinguishing mu1 from mu2 is this one. It simply encodes that the value at time point t0 is equal to y0. And then the relaxation basically encodes this tau epsilon window, which can't be matched by mu2, so mu2 doesn't satisfy the relaxation. And for the other direction, we take a formula which says that in this tau vicinity of t0, the value of the signal is within larger distance than epsilon from y0, and that there is actually some point in the time domain at t0. So mu2 obviously satisfies this, and the relaxation transforms this into a formula saying that at time point t0, the signal must have different value than y0, which doesn't hold for mu1. Now just a few words about the possible future work. Firstly, it would be good to have a full picture of all conformance relations based on the idea of tau epsilon closeness, because there are a few options depending on whether we choose to consider refinement or equivalence relation on the level of individual traces and systems. And in our paper, we studied only two of them. A different idea is the characterization of Skorhod metric, because so far there is only the preservation result by Deschmuck et al. For freeze LTL, but I expect it may be very challenging. And yet another direction is to consider a branching model with disturbance in time and value. And a quick summary of our work. So the key result of our article is the logical characterization of conformance relation that allows for disturbance in both value and time. And the characterization is achieved with syntactic relaxation of MTL, so we know precisely which properties we can expect to hold from a conforming system. And there is also a formal proof that an area relaxation operator from the literature can't provide the reflection property. I also wanted to mention that our theory used some, I think, nice solutions in terms of semantic and logic. We use time traces, which are very general, and we also have a variant of MTL with a few adjustments, and I think they may be useful in other contexts as well. That's all, and thank you very much.